One of the reasons that we want to introduce signed numbers is to simplify our discussion of change. In particular, to be able to talk about increasing and decreasing in the same way. In order to do this, we define the signed difference or signed change in a quantity. The signed difference between two values, or the signed change in a quantity, sometimes we call it the delta of the quantity, and write the Greek letter delta, which looks like a triangle. I'm only mentioning this now so that when you see it again, you'll have seen it before. The signed change in a quantity is given by later value minus earlier value, always in that order. Let's see what that implies. Suppose gas prices go from $2.79 to $2.83 per gallon. Then the signed change is the later value, $2.83, minus the earlier value, $2.79. These are positive numbers, bigger minus smaller. I don't need to do any messing around. I can just subtract. 13 minus 9 is 4. 7 minus 7 is 0. 2 minus 2 is 0. Drop down the decimal point. The signed change is 4 cents. This is an increase of 4 cents. The signed change is a positive number. On the other hand, suppose the price of a laptop goes from $399 to $285. The signed difference between those prices is the later price minus the earlier price. Oh, this is smaller minus bigger. So we'll need to write that as dropping the dollar signs. 285 plus negative 399. So these have opposite signs. The operation I want is subtraction. Bigger minus smaller, because that's how the algorithm works. 9 minus 5 is 4. 9 minus 8 is 1. 3 minus 2 is 1. And 399 is bigger than 285. So the answer is negative. This is a decrease, right, of $114. And so the signed change is negative. An increase is a positive signed change. A decrease is a negative signed change. Why is this useful? Well, remember before when we said once we know how much we change by, in order to get the final value, we add if it's an increase or subtract if it's a decrease? If we encode whether it's an increase or a decrease with the sign, we don't need to do that screwing around. It will always be the case that the final value equals the starting value plus the signed change. Notice that this really encodes the same fact as the signed change equals the final value minus the start value. This question asks, what do I need to add to my starting value in order to get the final value? This is just what subtraction means, these two sentences being equivalent. But this is kind of cool, right? Because then I don't have to do all of that fuzzy if stuff. So I'm going to give you, just for practice at this terminology, a problem where I ask you to find the signed change. Suppose the number of shops on Main Street goes from 217 to 196. Find the signed change. Pause the video and try this now. Alright, so we went from 217 to 196. 196 is the final value. 217 was the starting value. This is smaller minus bigger, so I need to do this as signed arithmetic. Now, opposite signs, positive plus negative. So what we want is subtraction. Bigger minus smaller, because that's how the algorithm works. 7 minus 6 is 1. 1 minus 9, can't do it, gotta borrow. 11 minus 9 is 2. 1 minus 1 is 0. So my answer is going to be some kind of 21. 217 is bigger than 196. So the negatives have it. The answer is negative 21. We can also use this to figure out where we end up, given where we start and how much we change. Suppose at noon the temperature is 28 degrees Fahrenheit. By midnight, it's changed to 37 degrees Fahrenheit. We want to know what the temperature is at midnight. Remember that final value is starting value plus signed change. Pause the video and try to find this. All right, so we start at 28 degrees Fahrenheit, and then we change by negative 37. So we'll have 28 plus negative 37. What do we get? These have opposite signs, so we want subtraction. 7 minus 8, can't do it, gotta borrow. 17 minus 8 is 9. 2 minus 2 is 0. So my answer is going to be some kind of 9. 37 is bigger, and 37 is negative, so it's going to be negative 9.